Okay, is the mic working? Yeah, it is. All right, thanks a lot for the invitation and for the nice introduction. It's very nice to be here. So I'll start this series of tutorials with the introduction to cluster and graph states, and then you'll hear from one of the inventors of measurement-based quantum computing about how to use them. So this is the outline of the tutorial. I'll first give you some motivating examples to kind of ease you into the topic. I will go over the stabilizer formalism and explain what stabilizer states are. So I'm not assuming familiarity with any of these things. It'll be at the quite introductory level. I'll define graph states. I'll disambiguate them from cluster states. Some people use the term interchangeably. I distinguish them. And I'll have a very brief discussion of measurement-based quantum computing, since you'll hear a whole lecture about it. I'll talk a little bit more about measurement-based repeaters for quantum networks. And then, time permitting, I'll talk about how we are trying to generate these kind of states, at least for photons. All right, so let's go ahead and start. So very basic slide, the idea of entanglement. You're probably all familiar with Bell states. One of the Bell states has this form, 0, 1, plus 1, 0. And of course, the point here is that you cannot write the state as a product state of 2 qubits. So in this state, there's inherent correlations that are non-classical, and measurement of 1 qubit determines the state of the other qubit. And of course, we can use all these properties for various things in quantum technologies. So I'll give some examples before I go and formalize things. So one example is something that's used a lot in quantum networks, and it's the idea of entanglement swapping. So you have 2 Bell pairs, and you can imagine that the purple and the blue qubits are in the same physical location, and the yellow and the green are far away from each other, and far away from the purple and the blue. Then we make a Bell state measurement, a Bell basis measurement on these 2 qubits, the middle ones, that are in the same location. And once you do that, what happens is, of course, the output of this measurement is a Bell state, right, by definition, because I'm measuring the basis. But what is pretty amazing is that the other 2 qubits end up also in a Bell state. So you build these correlations by consuming 2 Bell pairs and projecting into the Bell basis, and you create this extended Bell state between 2 qubits that have potentially never interacted with each other. Another well-known place where entanglement shows up very prominently, and I should say that this is kind of examples where you have entanglement and measurement together in their interplay, is teleportation, quantum teleportation. So here, first, you create a Bell state, which is shown here in the square. And then you bring in another qubit, which is in some arbitrary unknown state. So we don't assume anywhere in this protocol that we know what psi is. Then what we do is, so one of the 2 qubits of the Bell state can now be very far away, right? It's been entangled with the other qubit, and then it doesn't have to be in our lab anymore. The next step, the second CNOT and the Hadamard, followed by the single qubit measurements, together form a Bell state measurement, right? So when I say Bell state measurement in this talk, I'm going to mean essentially this box. When you do that, what happens is that the state psi that you started off on the first qubit, the top qubit, is now teleported on the last qubit, which again can be very far away, up to X and Z Pauli gates. But if we know, we know what the outcome of this Bell state measurement is, then we know what X and Z, whether an X and a Z have been gonna come together with this procedure, and we can undo them. So we can get exactly the state psi. Another place where entanglement shows up is, of course, quantum error correction, where we use highly entangled states and we just use a subspace of a many-qubit entangled, of a many-qubit Hilbert space, specific entangled states, and that subspace forms our code space. And again, measurement is very important here because we need to measure to see whether an error has occurred, and if so, which error or how to correct it. So these are kind of 3 motivating examples to kind of ease us into the idea that we're going to be using entanglement as a resource along with measurements. All right, so to do that, before I get into graph and cluster states, I want to give you an introduction on stabilizer states and the stabilizer formalism. So first, let me define the Pauli group. And if you're not too familiar with groups, all you need to know is the things in the bottom, right? A group is a set of elements that have some group operation. In this case, it'll be multiplication. And it's closed under this operation. So if I multiply 2 of these elements, I'm going to stay in the group. And there has to be an inverse and an identity in the group. And of course, I've put in the identity. OK, sorry, the pointer doesn't work. In the top line, you see the identity. And I'm also putting these phases in there, because when I multiply x and y, for example, I get a minus and a factor of I. OK, so I have the Pauli group. And then I can take tensor products of these things to create a Pauli group for n qubits. So in this example, I've listed all the possible terms inside the Pauli group for 2 qubits. And you see there's a lot, because it's all the combinations of x, y, and identity, x, y, z, and identity, and then the phase factors. Now, I can take a subset of the Pauli group such that the elements of that set commute. So the commutator is 0, and minus identity is not in this set. And the maximum independent set of these, when I say independent, is that you cannot generate one of these S sub i's by multiplying the others. So the maximum independent set is called the generating set. And what's special about these is that if I apply one of these elements onto a particular state, that's called the stabilizer state for the set, then I get back that state with eigenvalue 1. Right, so this is an eigenvalue equation where all these operators commute, so they have a common eigenstate, and the eigenvalue is 1. Right, that's it. So this is the definition of a stabilizer state. And it suffices to satisfy the equation I showed you over there for the generators. And the reason is that if I take this equation and I multiply by one of the stabilizers that is not in the generator set, and I'll show you an example in a moment, then the equation is automatically satisfied for these other elements as well. By the way, I'm also happy to share my slides with anybody who wants them later. All right, so let's look at a particular example, especially if you're not familiar with this. It always helps to look at an example. Let's consider the particular stabilizer group of 2 qubits that looks like identity tensor identity, right? I need the identity. X. So this notation just means X tensor X. So it's a 4-dimensional matrix. Z tensor Z and minus YY, right? So these you can check that they commute pairwise. And a nice trick to quickly check if 2 Pauli products, Pauli operators commute is to see in how many places do they fail to commute. So if they fail to commute in an even number of places, then they commute. If they fail to commute in an odd number, they anti-commute. Okay, so for example, XX and ZZ, qubit-wise, X and Z don't commute, right? The commutator is Y, proportional to Y. Same, of course, for the other qubit, but because they fail to commute on 2 qubits, the whole thing commutes. Does that make sense? Okay, great. All right, so this is a stabilizer group for 2 qubits. And now you can notice that I can obtain minus YY by multiplying XX and ZZ together. And I can also obtain the identity if I multiply xx with itself or zz with itself. So what that means is that I only need two of these elements, two of these operators, to define my group, my stabilizers, because I can get the others. So I call these the generating set, the generators. And it turns out, of course, that the state that these stabilize is the Bell state phi plus. Right? And let's actually check that together. So if I apply, let's do zz first. Right? If I apply z on 0, I get back 0. If I apply z on 1, I get minus 1. But now I'm applying z on both qubits. So from the second term, the 1, 1 term, I get minus 1, which of course squares to 1. Right? So phi plus is an eigenstate of zz. Also, I don't know what's the format, but if there's questions, I'm happy to take them as I go. I don't know how you did it in yesterday's lectures. Okay, great. Especially if there's something that you need me to clarify to keep following, please ask. Now let's look at xx. If I apply xx on 0, 0, that flips it to 1, 1. And vice versa. If I apply xx to 1, 1, I get 0, 0. So then I'm getting, the 0, 0 gives me 1, 1, the 1, 1 gives me 0, 0, and I get back the same state. Right, so these are clearly eigenstates with eigenvalue 1. Let's look at another example. Let's look at a well-known state that's sometimes called cat state or GHZ state, where I have a superposition of all the qubits being in state 0 plus all qubits being in state 1. Okay, so we can convince ourselves by inspection that the stabilizers I wrote down are really stabilizers of the state, right? So if I apply ZZ 22 qubits, the 0, 0, of course, gives me immediately 0, 0. The 1, 1, I get minus 1, minus 1, which, of course, multiplies to 1, 1. And the same thing for all the other terms, right? So, and you see that these are generators because then I can multiply them together in any way I like, and I get new stabilizers. So for example, let's take Z1, Z2, and the subscript here means which qubit I'm applying it to. Let's take Z1, Z2, and multiply with Z2, Z3. Okay. Then I'm going to get Z1, Z3. Z2 is going to square to identity, right? Yeah, this kind of works. Okay. So you can easily check that Zn minus 1 Zn is a stabilizer of the state. And you can also, of course, the product also automatically has to be a stabilizer. But you can also check we get new stabilizers, right? So this is a generating set. Now, X, I'm applying X on all the qubits. And similarly to the Bell state I showed you in the previous slide, I get, I see that this is an eigenstate of this operator. Okay, now consider the state, the same state, but now I put a minus sign over there, right? Is this now, is the state now stabilized by these operators or no? Sorry? Good, good, right? If you look at this one, this is what kind of, ruins this being stabilized because the Z, they have the same property, right? I just do parity check for any two qubits, it works. But now if I flip all the qubits, I get all ones from here, but then I get minus 0. So that is not a stabilizer. This set is not a stabilizer of the GHZ with a minus sign. So if I were to remove the last stabilizer from the set, the last generator, then I would stabilize a two-dimensional subspace and not a single state anymore. Right? Because removing this stabilizer over here, or this operator, would give me this set of Z operators. And these, of course, already stabilize this, and we already discussed it stabilize that. So I'm stabilizing two states. Right? So I'm removing one operator, and the Hilbert space that I stabilize grows. And why is this important? This is important because in quantum error correction, we want to define a qubit, a logical qubit, so we need to stabilize more than just a state. Right, so this formalism, of course, shows up all over quantum error correction, where we can define and stabilize our codes, the code subspace, to be the states that are stabilized by a set of operators. So let's look at an example. So let's think about one of the simplest possible codes, the 3-qubit repetition code. Right, so this is probably familiar to most people who have taken a quantum computing course. So I'm defining a logical 0 to be a tensor product of all the qubits in 0, and the logical 1 to be a tensor product of all the qubits in 1, right? And then what are the stabilizers for the subspace? It's really similar to the previous one. It's, again, products of z's, right? Because here I'm checking whether these two agree and whether these two agree pairwise, right? So these are generators. If I multiply them together, I'll also get z1, z3, which is, of course, also a stabilizer of the state. Now, a general logical state is going to be an arbitrary superposition of my two code words, my two states that I stabilize by these operators. And I also define logical operators. What do logical operators mean? It's operators that act as Pauli x's and y's, right? So if I take z1, z2, z3, and I apply it to this state, I just get back that state with eigenvalue 1. But if I apply it to this state, what do I get? I get a minus sign, right? So this acts as a logical z, as it should. Now, if I take a product of 3 x's, this goes to that and vice versa, right? So this acts as a logical x, as it should. And logical operators have to commute with the stabilizers, and here you can check again, they fail to commute. This fails to commute in 2 qubits, even number, so the whole thing commutes. Okay, another class that's worth defining here is Clifford operations. And Clifford operations, or Clifford gates, are special gates in quantum information processing. They are unitaries that take a Pauli product, a Pauli string, to another Pauli string, right? So all the operators we've seen so far, Z strings, X strings, combinations of those, with these particular operators that I call U over here, I would just get back another one. And what's important from our point of view here is that if I start from a state that's stabilized by a set of operators, and I apply a Clifford gate, I can do this trick to see what happens. I can insert here one of the stabilizers, because stabilizer on the stabilizer state just gives me back the state, so I can freely inject it if I wanted to. And then I'm going to also inject the identity in the form of U dagger U. And then what do we see? That we have an SI prime forming over here from this sandwich over here. And then I get back UC, which is the state psi prime, right? So I'm going to another stabilizer set and another stabilizer state through Clifford operators. And we're going to need later this information, some particular Clifford operations that are important and show up a lot in measurement-based quantum computing and measurement-based quantum information in general. Also the definition of graph states. So well-known Clifford gates are Hadamard, C0, and CZ. And what I'm going to show you now is what happens when I commute through gates like this that are Clifford through elements in a circuit. So here I have Pauli operators, and this shows up a lot in quantum error correction, where you want to see if there's an error on qubit, does it propagate and how to other qubits in my code and in my quantum computation, Okay, so what I mean by this diagram here is this. So if I have a Z gate that's followed by a Hadamard, I can pull the Z through, and that turns the Z into an X because I'm using this identity. So I can play a lot with the circuits this way and transform circuits to something that I can more easily calculate. So I hope this image here is clear what it means. It just means this, right? So this means if I pass X through, I'm going to get a Z. If I pass Z through, I get an X. Okay, now let's see what happens if I have something slightly more complicated, namely the C0 gate. And this is a control NOT gate where I have the control qubit to be 1 and the target qubit to be 2. So what happens if I have an X gate on qubit 1 sandwiched by these two C0s? What will happen is that the X will pass through and it will propagate on the other qubit as well. So you have X followed by C0. That's equivalent to having a C0 and then two X's on both qubits. So this is an example where if X was an error, it would spread to the other qubit through the C0 operation, right? And that's why we have to be careful when we come up with quantum error correction protocols so that the errors don't propagate freely to other qubits, or they propagate in a controlled way so that my operation remains fault tolerant and that I can catch the errors with my code. Here's another identity. Here I have, again, the same C0. Control is 1, target is 2. But now I have a 2 here, right, X2. Here nothing happens. This just propagates right through because X commutes. X on 2 commutes with C0. If I sandwich Z, Z1, I get this, right? The error commutes through. And if I sandwich Z2, then I get this correlated effect. Now what happens if instead of C0 I have a CZ gate, which is going to show up a lot in graph states and cluster states. If I have a CZ, so here I only have 2 identities instead of 4 because there's symmetry, right? CZ is a symmetric gate. It doesn't matter which is the control and what's the target, so I only need 2 identities to show this. So if I have a CZ, what happens? If I pass X through here, I get XZ. So I get my CZ, XZ, right? So here's another example where this gate propagates through their qubit. But if I just had Z, Z commutes with CZ, so it just passes right through. And we'll make use of this in a moment. Okay. Now, a very important thing about Clifford operations is that if you start with a stabilizer state, and without loss of generality, let's assume I start with all 0 state, because I can get a stabilizer state from the all 0 state with Cliffords, then I can simulate the circuit or the state, what happens to the state classically, efficiently. And the reason is that I'm tracking operators instead of states. And if you're familiar with Heisenberg picture, this is very similar to that. I'm leaving the state alone, and I'm seeing what transformations happen on my stabilizers. And that way, that allows us to simulate large-scale quantum error correction circuits. So I'm not going to go too much into this. This is kind of technical, but I just want to show it here in case you run into it, when you read papers. There's a nice formalism to represent stabilizers, where instead of having X and Z's, or X, Z's, and Y's, I have a tableau, and there's a row for each stabilizer. And then if I have an X, I put an identity, 1, the number 1 here, and 0 here. If I have a Z, I put 1 here and 0 here. And if I have Y, I put 1 in both. And then I need also some phase to track the phase. So this is a way that, it's maybe not familiar to everybody, but it's actually a way that you can keep track of the stabilizers and do operations on them and see what happens when you multiply things together. Right? It's used a lot in quantum error correction. There's also an open source package, very nice package from Google that I think a lot of people use. Okay, so now with this we're ready to look into a particular class of stabilizer states that are called graph states. So this takes me to the third part of the talk. So graph states, as the word implies, are states that can be represented with graphs. And every node in the graph is a qubit, and every edge corresponds to an entangling gate. So if someone gives you a graph, you can very easily write down the state by putting every qubit in state plus. This is unnormalized, you need to normalize it. And for every line you see, you do a CZ gate, which is, of course, this entangling gate over here. And this is a constructive definition of the graph, right? So now, with this rule, any graph you see, you can write down the corresponding graph state, right? And obviously, when CZ acts on two pluses, it creates entanglement. So this is going to be a highly entangled state in general. Now, we went through the pain of going over stabilizers and definitions for a reason. And that's because these states can also be defined in terms of stabilizers. So for every qubit, so I'm going to have n stabilizers for an n qubit state. And the way I'm writing the stabilizers down, I'm going to look at every qubit. And my stabilizer has x for that particular qubit. And for every neighbor it has, so this one, for example, is connected to 3 other qubits, I'm going to have a z. So here, for example, I have x, z, z, z. For this one that only has one neighbor, the stabilizer would be x, z. Okay, so the weight of stabilizers changes depending on the neighbors, but the form is the same. I have one x for every qubit and a z for the neighbors. Again, you can check, that this satisfies the equations we saw. Now, there's particular graph states that are of special importance and interest. And again, different people in the community use different conventions. I tend to use the word cluster state to denote a graph that corresponds to some regular lattice. So for example, here you could have a square lattice. Again, every circle here is a qubit. Lines denote entanglement the way I discussed. And for this, if this state is large enough, then you can run arbitrary quantum computation on it. And you'll hear a lot in the second lecture about that by one of the inventors. This is not the only state on which you can do quantum computing. There's other lattices. There's a 3-dimensional lattice, also called Rausendorf lattice, where you can do quantum computation in a fault-tolerant way. And then there's other lattices that have kind of stranger-looking structures. For example, this is called AKLT state. It's known from condensed matter physics. But the point here is that it's not only the 2D square lattice that's useful for quantum computing. Measurement-based quantum computing, this is just the most well-known. Okay, so again, this is my convention. I'm not sure, who agrees with that, but for me, the term cluster state refers to lattices. All right, let's now go and look at the stabilizers. And again, I told you already what the stabilizers are, but let's see how we can derive them. Okay, so remember the constructive definition of the graph state. Every qubit is put in the state plus. Plus is just 0 plus 1. And the state plus for a single qubit is stabilized by the operator x, right? If I apply x on 0 plus 1, I get back 0 plus 1, eigenvalue 1. But now I have n of these, so my stabilizers are just going to be moving the x on a different qubit. All right, so I'm going to have n of these, where the x moves around and identities on everything else. Okay. And now what do? I apply CZ. Let's see what happens if I apply CZ on the first 2 qubits. Right, so I'm going to apply CZs according to the edges. Yeah. Mm-hmm. Yes, so here I have n of them for n qubits, and that specifies the state. If I remove, then I increase the size by 2. Yeah. The generators are n, but you can multiply them and get, for free, new stabilizers, yes. But the generators, that's the max. Yeah. Okay, good, great. So again, I would apply CZs according to the graph, right? So first, let's just apply CZ on the first 2 qubits, just to see what happens. And because there's so much symmetry here, if I figure out what happens to the first 2 qubits, I can figure out the rest, right? So this suffices. So if I apply CZ, by definition, we get the graph state because I told you that's how I define it. So I get G0, a graph state that has a connection between the 2 qubits. All the other qubits are unentangled. So that's what I get. And now let's see how it works with the stabilizers. So I have my stabilized state that I started with, which is just a product state of all pluses. And now I apply this CZ12 on this. Now I'm going to track the stabilizers, right? So I do this trick I showed you before. I just put CZ times CZ, which is the identity. So this I get for free. And why do I care to do that? Because CZ12 on C0 is just G0, right here. So now this will have to be the stabilizer, because I have an operator acting on a state equals that state. So now I'm going to see what are the stabilizers. So I'm kind of going from the left-hand side of the definition of a graph state to the right-hand side, where I show you what the stabilizers are. Okay. Again, this is the stabilizer. This is the state G0. Now we use the relationship we showed earlier, where CZ, gives me gives me XZ, right? So I pass this through, I get XZ, and then I see that the stabilizer is X tensor Z, identity, and all the rest. Right, so from this constructive definition, I could derive the stabilizers. Let's look at some examples. So let's look at a 3-qubit linear graph state. So these are 3 qubits in a line. I can write this down in a sort of more economical way by mixing the plus, minus, and the 0-1 basis. If I were to write everything in the 0-1 basis, I would get more terms. So if you use the computational basis, this gets pretty expensive pretty quickly. But we know it doesn't have to because these are stabilizer states, right? So just by staring at the state, I wouldn't necessarily know how to, that I have an economical way to write this. And this is an eigenstate of the following operators. Again, the definition, right? This is X, Z, so I have X1, Z2. And then I have one, this is connected to 2 qubits, so it's ZXZ, and then ZX for that one, right? So again, I have 3. I can multiply them to get more. One thing to notice that I think sometimes is confusing to people who get into this field is that just by counting edges, you cannot conclude something about the amount of entanglement. And here's an example of this. Let's look at this that only has 2 edges, and this state that has 3 edges. If I were to construct this by putting every qubit in state plus and then doing CZ gates, I would indeed need 2 CZ gates here and 3 here. But there's equivalent ways of making these states that do not require that. Actually, these 2 are locally equivalent, which means I can do single qubit gates and go from the one to the other. So both kind of the visual of having 3 edges here versus 2 and the constructive definition are somewhat misleading in that they might lead me to think that, oh, this needs more entangling gates to create, which is not the case. Okay, of course you can create it with 3, but in a realistic scenario, maybe that's not what you want to do because you can create this and then do single qubit gates. Another primitive that comes also from graph theory is something called local complementation. And this is complementing a node by creating or removing edges between the nodes that are unconnected or connected neighbors. That's a mouthful, so let me show you. I'll show you an example in a minute. So in graph states, in the quantum context, local complementation is equivalent to local Clifford gates. And there's something called an orbit, which is all the possible states I can get if I do local complementation on a particular graph. So I start with that graph, and what I do, I look at a node, and then I look at its neighbors. And depending on if these neighbors are connected or disconnected, I either create or remove or create a line between them. I'll show you an example. And there's also a nice algorithm that you can use to check if two graphs are LC equivalent. So let's look at a particular example. Let's take 4 qubits. And then what I'm going to do is I'm going to look at this, right? And then I'm going to do local complementation. I believe this is done around 3. So let's look at qubit 3. Has 2 neighbors. The neighbors are not connected to each other, right? 2 and 4 don't have an edge. So I create an edge. And then I keep going. I circle through all qubits, and so it's a lot, right? You see already with 4 qubits, I have a very large number. So just like exhaustively writing all them down is not efficient, but it's kind of instructive to see for this example. And here, because I've numbered qubits, they're in equivalent graphs, right? So here, 1 and 2 have switched places. Yeah. Yes, you can do it with single qubit gates. Yeah, so that's the point, right? This looks more entangled than this, but in fact it's not because they're unitary equivalent. Yeah, so there's a rule about which gate you would use. I believe it's Y, but I'm not entirely sure. Yeah. Yeah. And actually, if you're interested in this topic, this is a really nice, comprehensive paper. It's super long, has everything, all the rules about graph states, about measurement, etc. And again, if you email me, or I can send the slides to the organizers, I'm very happy to share them with you. And there's a lot of references here. Right. So I think this is a nice example because if you were to construct this, you would need a lot of CZs, fewer here, but again, you can go from the one to the other. Now let's look at linear cluster states of various lengths. We saw this example. This is in fact locally equivalent to a 3-qubit GHZ state. So this is the same class as GHZ states. And both, of course, for this state and GHZ state, there exists a single qubit measurement that destroys all the entanglement. Now consider just something very slightly more complicated, like a 4-qubit linear cluster state. Again, I'm writing it in an economical way where I'm mixing 0, 1, and plus minus bases. Otherwise, I would have more terms, right? So I'm kind of sparing us from that. And with writing it this way, it's also easier for you to check that this is an eigenstate of the stabilizers that I showed you. Because you can easily, what X does on the 0-1 basis, what it does to the plus-minus basis, there's fewer terms, so it's easy to see which one goes to which under the stabilizers and how I get back the state with eigenvalue 1. So this one is not equivalent to a 4-qubit GHZ state. It's a different class. So in a GHZ state, a single qubit computational basis measurement destroys all the entanglement, right? Because I have all zeros plus all ones. If I measure 1 qubit, doesn't matter which one, I'm going to collapse the whole state into a product state, right? If I get back 0, everything will be in 0. If I get 1, all the qubits will be in 1. In this case, it's not the case, right? You can easily check that if you measure, let's say, this qubit in the computational basis, you have some residual entanglement on the other qubits. So yeah, here's spelled out. So let's say I measure the 4th qubit. I get outcome 0. Let's look at the state. The first term and the third term are compatible with that measurement, right? So my post-measurement state will be a linear superposition of the first and the third state. And what remains is a 3-qubit cluster state, because I get plus 0 plus, plus minus, 1 minus, which if I stare at this here is exactly a 3-qubit linear cluster, right? And if I get 1 over here, let's see what I get. Then I get the second plus the last term, which is plus 0 minus, plus minus 1 plus. It's almost a linear cluster state up to a Z gate on qubit 3. So this is reminiscent of teleportation, right? I make a measurement that has a probabilistic outcome, and then I can go and correct to get exactly the state I was aiming for. It's very similar. Now imagine we're measuring the X basis, and I guess for simplicity, state 1, there's a lot of symmetry, so you can rewrite this in a way that shows the symmetry explicitly, but let's look at measuring the first qubit, since I've explicitly used a plus-minus basis for this. If I measure in X, what happens? Let's say I get plus. You see that I get the first and the second terms. But for the first and the second terms, the second qubit is in state 0. So now by measuring in X, I'm also destroying the entanglement of the second qubit with the rest. But what do I get for the other two? I get plus 0, plus minus 1, which is equivalent to what state? A 2-qubit. So I have plus 0, plus minus 1. It's equivalent to Bell state, right? It's a Bell state up to an X gate. So this measurement, this decouples these 2 qubits, but gives me back a Bell state, or doesn't touch the entanglement in those. And in general, Pauli measurements on stabilizer states will always leave behind a stabilizer state on the unmeasured qubits. And if I want specifically a graph state, I can go and do my corrections and get the graph state. So let's now look at what different Pauli measurements do. So I purposely drew here a graph that's somewhat complicated, doesn't have a regular structure. So if I measure in the Z basis, I'm of course disentangling that qubit. Any projective measurement will. And this will be, I drew this as a graph, but we have to remind ourselves that this will be up to some Pauli corrections, right, to bring it explicitly into a graph state. So here, what would I have to do? I measure in the Z basis. For this to be a proper graph, even if it's a 1-node graph, what gate would I have to do? So it'd be either 0 or 1, but what we run this to be in state plus. So I need a Hadamard, right? At least a Hadamard, very least a Hadamard, right? And I might also need a Z gate on top of that. All right, and then what happens to the rest? The rest of the graph remains intact, again, up to single qubit Paulis. But what's important here is that the structure is very specific, and I can sort of make use of these rules when I try to calculate things in various quantum tasks. Now let's look at the Y measurement. If I measure this qubit in Y, again, I'm disentangling it up to Paulis. I get a graph for this, just a node. And now I do local complementation to the neighbors. And remember, local complementation means if the neighbors are not connected, here they're not, I put an edge. If the neighbors are connected, like I show here, then I remove the edge. So this Pauli measurement also leaves, the graph structure, but it modifies it. And again, I would need Pauli operations to bring it exactly into a graph form, but you see what happens to the structure. And X measurement's a little bit more complicated, so I'm going to show you what we'll need next. We're going to be using 2X measurements in neighboring qubits. 2X measurements in neighboring qubits remove those qubits, and they couple the neighbors. So this is also reminiscent of teleportation, right? I'm measuring these two, and I'm creating a line between these two. I'll come back to this later. Okay. And then, of course, I don't only want to do Pauli measurements because I want to go beyond Clifford gates. I want to do something less trivial. So to get generalized rotations, more kind of different things outside the Clifford group, I would need non-Pauli measurements. And I'll show you a little bit of that. You'll hear more in the next lecture. Now, let's go back to this point of Bell state measurement. What is a Bell state measurement? Mathematically, it is represented by 4 projectors. It's a 4-dimensional Hilbert space. These are orthogonal states. If I measure in the Bell basis, I have to end up in a Bell state. So these states are projectors onto the Bell states. And how do I do a Bell state measurement? Right, we saw this a little bit in the teleportation circuit. I need to combine Hadamarts and C-naughts. Right, so if you remember the teleportation circuit, I had a C-naught followed by Hadamard followed by single cubic gates. This is the same to saying, how do I go from this basis that's entangled to the computational basis? Because usually measurement is in the computational basis. And if I want to measure in a different basis, I need the unitary that rotates me to that basis. Not always. There might be experiments where you can do it differently. But from a mathematical standpoint, I can write down these identities. So look what's happening here, right? I have my 2 qubits that I want to measure in the Bell basis. I do a C-naught. I do a Hadamard. I project onto this separable basis, i.e. I measure in the computational basis. And then I restore the Bell states, right? That's mathematically, hopefully this is easy to follow. Let's look at this now in the context of entanglement swapping. I have 2 Bell states. And the first step is that I follow this here. I do a C-naught between the 2 qubits I want to measure. I do a C-naught here. Generically, that creates entanglement. Okay, possibly I also need the Hadamard, but this creates entanglement between these 2 qubits. Before I measure, if I am to follow this recipe for measuring the Bell basis, before I measure these 2 in the computational basis, I have more or less created a linear cluster state. So now you can kind of view teleportation from this lens of a cluster state, where I sort of intermediately create a state that's equivalent to a graph, a stabilizer state, and then I measure these 2 in the single qubit basis. And then we can use the rules for Pauli measurements. And that, of course, disentangles those 2 qubits and creates this entanglement. Now, to wrap up the whole thing, I would have to go and redo this unitary here, and I would create entanglement here as well. Right? But this is a way to view entanglement swapping from the lens of a cluster state question. Mm-hmm. You asked if this would create an edge here. Oh, the first and the last, yes, because there's a lot of symmetry here. Yeah. But I'm assuming... Yes, so, okay. So maybe just to, in case it's a little bit confusing, here I'm a little bit abusing the notation in the sense that these are equivalent to graph states, but they don't have to be, right? I can write this as a 0, 0, plus 1, 1, which to bring it to a graph state form, I would have to do a Hadamard gate on one of the qubits. And then I would apply these rules. Right. So really you have to be careful with the single qubit gates, which I've not here, because I want to more show the concept rather than following the calculation. Right, but that's the idea here, right? That I need, at least mathematically, I need an entangling gate to make this measurement, and at the intermediate stage, I am creating a 4-qubit entangled state. So this is a little bit now looking like, in some way, teleportation, not quite, right? Because I'm not teleporting a state, I'm creating an entanglement. But you can assume that the yellow and the green are far away from each other, and I'm following exactly the entanglement swapping paradigm. So this part of the talk will be brief because you have a whole lecture, by the expert in the world on this, but I just want to give you a little bit of some elements. You'll probably hear it again, some of this, but I think it's, from a summer school point of view, it's good to have a little bit of repetition, not too much. So let's now look at, sorry, this was taken from earlier in the talk. That's why ignore this example thing. So let's look at single qubit gate teleportation. So let's take a qubit and put it in arbitrary state, psi, right, alpha 0 plus beta 1, and another qubit in state plus. If I want to create a graph state exactly, both would be in plus, and I do a CZ. But here I'm allowing one of the two qubits to be in a more general state. So alpha and beta can be anything. And then I do a CZ gate between them. So it looks a lot like creating a graph state, and I get this state. Right, so if alpha and beta, they're both 1 root 2, then this is exactly a graph state. Now, I'm going to measure the first qubit, meaning the one that started off in state psi, in this basis. So if you think of Bloch sphere, what is this basis? It's a basis that lives on the equator, and it rotates away from x toward y by this angle phi here, right? So if phi is 0, this is the plus-minus basis. So now I'm doing something that's a little bit more complicated. I'm not measuring anymore in the XYZ basis. I'm measuring in a rotated basis. And I'm bringing in this parameter phi. If I do that, the second qubit collapses into one of these two states. Alpha plus or minus e to the I phi beta minus. So what do we see here? The coefficients that were carried by the first qubit before are now carried by the second qubit. So this is some sort of teleportation, right? The information has been moved over. But it's not the way it was. There's also this phi over here. So this is teleportation up to a gate. And you can think of this as gate teleportation. I'm measuring this qubit that was originally in state psi before I entangled it. I'm measuring it in the correct way. I'm moving the state there with a unitary acting on it. And if I ask, what is the state of the second qubit after all this has happened, I get this. So you see UZ phi is the rotation about the z-axis by angle phi. But then I also have these byproducts. I have a Hadamard, and I possibly have an X gate. And what do I mean possibly have an X gate? This measurement is probabilistic. So I'll get either this or that. And depending on which state I get, I might or might not have an X gate on the other qubit. And again, this is really similar to quantum teleportation, where you project in the Bell basis, and the qubit that usually we say belongs to Bob collapses to a state up to an X and a Z, possibly. Right? Very similar here. So this is a very simple example of a gate teleportation. It's kind of a trivial quantum computation, but it's still exciting that you can use pre-existing entanglement and measurement to do a gate on a qubit. Now you can make this a little bit more complicated, because what I showed you, you can only do Z gates. You might want a general rotation. So you have your psi, you do your CZ gates, the remaining qubits are starting off in plus. And now you can get a generalized rotation by doing the right sequence of measurements. So now I'm going to measure in more bases and more qubits, and I'm going to push over the information to the last qubit while also doing gates on it. And you can use Euler decomposition. This is a little bit detailed. I'm not going to go too much into this, but there exists a recipe where it tells you, this notation says measure in the equator. That's what pi half means. Phi 1, phi 2, phi 3 means where in the equator I am. So if you combine all this, make these measurements, the last qubit is left in this state. So you see that I get my gate, which is the combination of ZXZ. But now my angle of rotation is a little bit different, right? I have these M's. So if my target was angle phi 2, I might get minus phi 2 or minus phi 3. How do I deal with that? I know the outcome of each measurement. right? So I measure the first qubit. I know what I get. So I know how to modify the next measurement, right? So I can undo these m's just by adjusting this basis, the measurement basis. And this is what we call classical feed forward, right? I don't have to do a quantum gate between these qubits. I just need to adjust something based on classical knowledge that was obtained from the experiment. Okay. Okay, so this is what this says, right? So for these non-Clifford gates, I need to do this classical feed forward. All right, this I'm just gonna flash. I'm sure you'll hear more in the next talk, but you can also do 2-qubit gates if you have a more complicated structure. I'll skip it since you'll hear more. And then, just to wrap up the measurement-based quantum computing section, let me just kind of recap the more familiar paradigm of a circuit model versus the measurement-based model. So in the circuit model, you start with a product state, typically all 0. You do single and 2-qubit gates, and you build entanglement through these gates. And at the end, you do single-qubit measurements, right? So let's ignore for now quantum error correction. All the measurement happens at the end, right? Algorithmically, the measurements happen at the end. Now, in the cluster state model, measurement-based model, all the qubits start in this highly entangled cluster state. And then the computation itself amounts to single-qubit measurements in this feed-forward operation. And again, you end with single-qubit measurements at the very last qubits. So you can think of this as a spatial versus temporal resource. When you do circuit model, the qubits are all the same, right? It's a fixed number. And then you just do gates and time on them. Here, you have already these qubits to be entangled, so you can think of the spatial dimension going this way, horizontally, as the temporal dimension here. And of course, as you go along, you consume the entanglement you build up initially. Okay, so some considerations. You don't need necessarily to create the whole state up front, so that alleviates some of the difficulty. For the photonic case, this allows for some probabilistic gates to happen offline and repeat until success. And from practical point of view, the measurement needs to be fast compared to the coherence. And of course, electronics have to be fast to implement feed forward. So there's some things to consider if you're trying to actually do this in the lab. Now there's a modified version of the protocol I showed you, which is called fusion-based quantum computing. And it was modifying essentially the cluster state quantum computing paradigm. It's what PsiQuantum focuses on. So instead of having this large 2D cluster state, what they are trying to do is create these smaller resource states and then do Bell state measurements between qubits in this lattice kind of structure. And if you make these Bell state measurements correctly, or generalized Bell state measurements, you could bring in parameters through these measurements, you can show that you can run an algorithm equivalently. So what are the differences here? Here, there's a lattice that's created dynamically in time, and there are entangling gates happening during the computation, right? Unlike the cluster state case where you create all the entanglement up front. There are quantum error correcting encoded variants shown here. So this is not the only state they're looking to create. But the point is that this is a fixed size, meaning it doesn't matter what algorithm you're trying to run, your resource state will have a fixed size. Right? Of course, you have to pay the price of Bell state entangling gates, Bell state measurements dynamically. Right? So there's this trade-off. And then, I already mentioned that photons are the most prevalent platform for measurement-based quantum computing. One big obstacle is that linear optics does not allow you deterministic entangling gates. Of course, the fact that you can generate entanglement offline helps with that. And single qubit measurements, change of basis, is relatively easy for photons. And feed forward is doable. There's also been papers on doing this on atomic qubits. And these are some experiments. This list is by no means exhaustive, so I don't want to annoy anybody. It's just some representative list on different platforms. All right, so let's look at the Bell state measurement. I mentioned that it's probabilistic. So the rest of the talk is going to be on photons. So now I'm kind of stepping away from the more abstract things and looking at more practical considerations, right? If I want to build these technologies from photons, what do I have to worry about? One thing you have to worry about is that with linear optics, your gates will need measurement and heralding. And there's some issues that come along with this, right? So let me talk about photonic repeaters and quantum networks and show you how we're trying to address these issues in that context. A lot of this will also be relevant in quantum computing, right? But I'm focusing on networks as a specific application. So in quantum networks, the prototypical thing I want to do is I have Alice and Bob who are far away, and they want to share at least one entangled state, in reality more. So we talked a lot about Bell states. So the simplest thing that they can do is Alice can prepare a Bell state of photons, or an atom and a photon, and then she can send Bob the other photon. There's a big problem with this, is that you cannot scale it, because photons are lost when they're transmitted either in free space or optical fibers. I'm going to be mostly thinking about optical fibers here. And in this case, about 99% probability of loss in 100 kilometers. So this is pretty bad, right? If you want to do something larger scale, it's a problem. Classically, you can measure and amplify. In quantum, of course, you cannot, because measurement alters the state. So you need to do something better than that. One thing you can do is you can put someone in the middle. Let's call them Charlie. And Charlie can create a Bell pair and send one photon one way, one photon the other. But of course, this doesn't scale, because this just cuts the distance in half. And if my problem is that things are bad exponentially, a factor of 2 in distance is not going to save me, right? But I can do something that we essentially already saw. I can use entanglement swapping. So now I'm going to have a Charlie over here and a Charlie over there, and I'm going to have another person in the middle. And there are 2 Bell states, one generated by this one by that one. And the person in the middle gets the photons, 2 of the photons, that are originally unentangled, and you can probably guess where this is going, make a Bell state measurement between them, and that way create an entangled Bell state here and propagate the entanglement out to these 2. Right? So now you can scale this approach the following way. Sorry, first I should say that this succeeds probabilistically for the same reason I showed you before. And the reason, what you can do to fix this or to address this is to use quantum memories. So if a Bell state measurement does not succeed, you can keep trying. And the ones that do succeed and create an entangling line, you can store them in a system that's long-lived. So let's see how this works pictorially. Yeah. It doesn't matter. So all work, but they should know the protocol. So it works for all Bell states, but in the end of the day, you have to know which one. You have to know the measurement outcomes. Yeah. So let's look at this, right? I have memory qubits. And in every node, in the middle nodes, I have 2 memory qubits. And you see, these are not entangled. So every memory qubit, think of it as an atom or a quantum dot, can generate a photon. So I can get a spin photon entangled Bell state. The photons are, of course, flying qubits, so I can send them to a Bell state measurement node. So you see the green ones, the red square indicates that they're in the same location. And now I can make measurements. Whenever this measurement succeeds, and this measurement succeeds to adjacent measurements, I can notify the node that sent this and that photon. And the node in the middle that holds the memory qubits can now make a Bell state measurement between them. So I'm doing entanglement swapping after entanglement swapping, right? But the advantage here is that I can have now the luxury of some of these Bell state measurements failing because I'm storing the entanglement on quantum memories. So once I make this measurement, I'm connecting this line. Then I also need to connect that once it succeeds, etc. So in principle, I can get this long line that connects two qubits that are far away, right? By just breaking up the distance. So we need at least 2 matter qubits per node. In practice, I probably need more, right? Because I need to do some sort of error mitigation or error correction. There's a very famous now experiment from more than about 10 years ago by the Delft group, and since there's been more experiments where they showed establishing entanglement for entanglement swapping between nodes A and B. So here they had an MV center here, an MV center there, each emits photons. Again, this was probabilistic. This Bell state measurement in node C probabilistic, but once it succeeds, they measured and verified that A and B were entangled with each other, as they should. Now, of course, this is a primitive. Again, there's been more work, but it's still a few nodes, right? And there's been many years from that. So even though this is the vision for a quantum internet, spans Europe, we're still not there. And the reason is that you need very long-lived quantum memories. This is one of the challenges. And that's, we're not there yet. So to go from a proof of principle lab demonstration to a practical technology, we need to deal with these issues. And one way that's been proposed to deal with these issues is that, okay, since we don't have good quantum memories yet, let's see if we can do without the quantum memories. And that's where graph states come back in. So I'll show you one approach. There's many variations of this. So here's what you could do. At every node in the network, you can create a photonic graph state like this. Let's not worry yet how you create it. But let's say you had the ability to create it. And you see there's a lot of arms over here, and we're going to make use of that. Sorry to have to switch view, but there's some issue with the next slide. So let me, again, walk you through the slide because it's a little bit more complicated. So the blue node is where I create this graph state. And now we know what this graph state is, right? I could write it down. It'd be painful to write it down, but I can write it down with stabilizers and it won't be bad. I create the same state in the other node, and then I send all the photons of one side to a middle node and all of them to another. So the node that normally would have a quantum memory now is empty. Once the photons are gone, it doesn't have any qubits. The qubits are collected half from this side, half from that, in these measurement nodes. And now we're going to do Bell state measurements again, because that's what we know creates entangling links. But now notice that I have redundancy. I can try this one. If this fails, I can try that one. If this fails, I can try that one. Right, so this is one thing I gain. But I can also make further use of my graph state rules. And let's say this worked. Let's say I managed to get the successful Bell state measurement here. What would I need to do? I need to get rid of the photons that live in between so that only Alice and Bob share an entangled state. Well, we can use the rules we know, which are X and Z measurements. So Z measurements remove, if you remember that graph from several slides ago, remove qubits from the graph. They don't mess up the graph structure. X measurements, on the other hand, connect my graph. So the qubits that are neighbors of the ones where the Bell state measurement succeeded, I can X measure, and that creates a link. All the rest I can Z measure, and that gets rid of them. So this brings in advantages. One is that I don't need to classical signal because there's nothing in this node. I just need Alice and Bob to know my measurement outcomes. And there's this redundancy for the Bell state measurement, which was my difficult part. But of course, we're not quite done, because I have implicitly assumed something. I've assumed that if my Bell state measurement succeeds, the neighboring qubits are there to be measured in the right basis. But they might not be, right? They might be lost, because those are also physical photons that we know are lost. So what we can do is we can modify the graph and encode these inner qubits. And notice that only the inner qubits really need to make it, because if one of these is lost, I can just go and measure another. So the outer qubits don't need to be as robust as the inner ones. And one code you can use, one encoding, is something called the tree code, tree encoding, where I replace a physical qubit with this logical qubit. And this is like in a graph state. It follows exactly the rules we saw. So if I were to draw this explicitly by inserting this tree, I get something much more complicated looking. And this whole thing here, this collection of qubits, is my logical encoded state. Now, I'll show you briefly, before I wrap up, why this works. So this code was introduced by Terry Rudolph and collaborators, and it has the structure. It looks like a tree, of course. So there's a branching ratio, tells me how many branches every qubit has, and the depth. And this is very highly loss tolerant. So let's try to use the things we saw from graph state rules to understand a little bit the loss tolerance. So what I would want is to make a Z measurement on the qubit that's represented by this whole thing. What could I do? If I measure all the top qubits in Z, then I'm done, because I disentangle them. So Z measurement disentangles, right? So it would suffice to make a Z measurement. But again, these could be lost. So let's imagine I try to do a Z measurement here, and I notice that this qubit is not there. I can use the beauty of stabilizer states and graph states by reminding myself that there's a stabilizer that's Z, X, Z, Z, right? So I take this qubit as a node, and I put Z's in all the neighbors. This is one of the stabilizers. Yes? And I want to measure this one. If I were to measure the other three, the purple ones, in the corresponding bases, that would give me their plus or minus 1, and it would have to perfectly correlate with the red one that I want to measure in Z, right? So if I can measure the stabilizer in many different ways, right? I can measure each qubit, or I can measure this thing collectively. Let's say I measure just the purple ones. If I get a minus 1, then I know that this Z measurement should also give me minus 1, because this is a stabilizer, and the whole thing has to be 1. If I get a plus 1 from this measurement, then I would know that this is plus 1. So this is an indirect measurement that I can do even if the thing I'm trying to measure is lost. Right? Of course, I'm assuming there's no other errors happening here, right? Because if there are, then this whole thing goes away. But I do have redundancy, so I can also check, do these also agree? And I can have a larger branching ratio and check further. And in the original paper, they also call this counterfactual measurement, which, okay, alludes a bit to quantum foundations. I think indirect is explanatory enough. Right, so the idea here is that we can recover the Z measurement. Now what happens if I want to measure X and my qubit is lost? I go and I try to measure it in X. If it's there, I'm done. I measure the rest in Z, and I'm done. And then I measure the others in Z, and I disentangle these. If, however, I try to measure it in X and it's lost, I can say, okay, I could just measure it in Z. It's not there, but I'll measure it indirectly in Z, and keep going until I find one that's there, and I can measure in X. So the X is not as robust as Z in the sense that I'm not using the stabilizer, but I'm assisting myself with Z measurements to remove the qubits that are not there, and then hope that this is, if this branching ratio is large enough, I will eventually find a photon that's not lost and measure it in X. And I can remove all the remaining ones with Z direct or indirect measurements. So this is summarizing this protocol. I start with the first qubit. I attempt the next measurement. If it succeeds, I'm done. I measure everything else in Z, directly or indirectly. If the first qubit is lost, I measure it indirectly in Z by using its children qubits here. And then I just repeat until 1x succeeds, and the rest are measured in Z. All right, so I think maybe we have another 15 minutes. 10 minutes, OK. I'll flash this quickly. So this is not as technical as some of the other things I presented. And this part is just how do we generate these states? Right? We saw that if I am able to generate states like these, I can do very powerful things. I can do universal quantum computing. I can create quantum networks. But we still don't have these things. So why, right? So the problem is, one of the problems is how to create entangled state of photons. One way is to use some nonlinearity, some matter qubit, where I pump it in a way and I create an entangled pair. There's many variations of this. Another way that I already referred to is to start from single photons, pass them through beam splitters, measure a subset of the photons, and conditionally on the outcome of those measurements, I get a graph state on the remaining. So, and then if I were, so I can also combine Bell states, pass part of the Bell state through the beam splitter and connect the chain. So let me go to this to show you the problem. Let's say I wanted to generate a pretty modest thing, a 3-photon GHZ state, right? Just small resource state. I can start with 6 photons, pass them through beam splitters, and measure 3 of them, right? So I'm measuring this, this, and that. Then, with probability 1/32, the remaining ones are in a GHZ, 3-qubit GHZ state. So you see how small this number is, right? I'm consuming 3 photons, and I'm also paying the price of a really, really small probability, just to create a 3-photon GHZ. And there's an analysis based on creating entanglement this way that said, OK, let's take those repeater states that I showed you, these complicated graphs with the arms, and ask ourselves, if I were to use this procedure in a quantum network, what resources would I need? And what they found is that to beat the limit of no repeater at all, just free sending the photon, I would need 1 million single photon sources per node. So on the one hand, I'm getting rid of quantum memory. That's on the order of several quantum memories. But I would have to pay the staggeringly large price of 1 million single photon sources per node, which is not realistic. Something you could do instead is follow a very nice protocol developed by Sean and collaborators from about 20 years ago, where they said, if I have a multi-qubit state like an atom in a cavity, and I pump it in the right way, I can extract photons. And this was quite a formal paper. They used matrix product state formalism to show this. But you can make it kind of more closer to the physical system. And that's what was done by a few people. I'll show you in a moment one example. So let's take an atomic system or a quantum dot that has a lambda structure. And I put it in the excited state. I can get a Bell state of the spin and the photon by spontaneous emission. If I have something a little bit more complicated, and I have now 2 paths, by the way, I can create this through this if I do pi rotations here, but let's just look at this. I can get GHZ states. And in fact, if I allow myself a Hadamard gate in the ground state, I can also get a linear cluster state. And this paper was put forward by Linda and Rudolph. There's been a lot of interest in the community on how can I use matter qubits that in principle emit photons deterministically to create interesting states like this. And there's been a lot of experimental activity. There's an early experiment by David Gershoni's group using quantum dots. There's also interest from the microwave community, superconducting qubits. There's very nice experiments by the Rempe group nearby, where they used atoms to create these states, and also by Pascal Senelar and Quandela, where they have quantum dots in a cavity and they can extract these photons fast. Right, so here you're trying to alleviate the problem of the probabilistic generation of photon-photon entanglement by using the matter qubit as an emitter. And all this is for single linear cluster states. You can also entangle emitters and emit entangled photons. So some of our early work used this idea, so you could get a 2 by n entangled state this way. Now let's look at the repeater states I showed you. It turns out you only need 2 qubits to get it. So you can entangle 2 qubits, one emitter, one ancilla, pump photons, and you can get an arm. Then you can make a Z measurement, remember the rules, that disentangles and does not disturb the structure. And then I can repeat this entangling gate, pumping event, I can get another arm. And I can keep going, and I can get this complicated thing I was looking for by also using the Y measurement, which, if you recall, did local complementation to the node. So by using sort of a clever trick of how I generate photons and how I measure and which qubits I measure when, I can in principle get the state with just 2 qubits. Now, of course, we said we wanted to the encoded version of this. And you can also generalize your protocol, use more emitters to get the state like that. I'm not going to take you through the details. You can also have one-way repeaters where you want to send a state and not necessarily share entanglement. So you can create these 3 states in a similar way and just send them along. So to wrap up, let me show you one last bit here. So I might want to create a more general graph state, right? I showed you recipes for one-dimensional, I showed you for GHZ, 2 by n, and this repeater state. But there's work that shows that maybe other states are more amenable to kind of as being good candidates for quantum networks. So for example, this recent paper. So it's a reasonable thing to ask the question, if someone gives me a state that's a good resource for some quantum technology task, how do I generate it if I were to generate it deterministically? And we answered this in this following paper. I'm just going to give you the highlights, and then if anybody's interested, I can talk about it offline. So the goal here is to create an arbitrary photonic graph state that's emitted from quantum emitters. And I can ask how many quantum emitters do I need, and what do I need to do to them? So you can think of this a little bit as a compilation problem. My target state is some final state, and I want to have a circuit that creates it. It's a little bit different than circuit compilation in that it's more restricted. So the photons can only undergo one gate, which is one 2-qubit gate, which is the gate that generated them. Emitting a photon, you can think of it as an entangling gate. There's non-unitarity. I can measure qubits as I like. The Hilbert space, I start without photons. And of course, photons don't interact with each other, so that's a problem we're trying to solve. So let me show you just a reference and the general idea. I start from the graph states, photonic graph state I want to create. And then I measure, there's a quantity that's called height functions related to the entropy. And I look at the entropy between every part. And that's the maximum of this function tells me how many emitters I need. And then the next key thing is I do a reverse engineering approach. So I start with the graph state I want to create on the photons and the emitters. And I go backwards. And I ask, how do I need to bring the emitters back into my state? We call this a reverse measurement. And how do I need to absorb the photons, because I'm going this way, instead of emitting them? And you can formalize this very nicely by using the stabilizer formalism and make the problem very systematic. So I'm not going to go through the details, but I just want to show you that you can do that. And then you can analyze all kinds of graph states. Someone can give you a complicated photonic graph state, and then this algorithm allows you to come up with a circuit that creates it from a quantum emitter, or a bunch of emitters in general. So I'll skip this, and I'll just leave you with some resources. Again, this is not an exhaustive list. There's many nice review papers, and of course, original papers. I followed this quite a bit in the stabilizer discussion. I think it's a nice, very nice reference. It's concise, so if you're already somewhat familiar, hopefully you are after this lecture. I think this book, it's also available on the archive for free. And of course, Robert's YouTube channel has very nice videos and introduction to graph states and measurement-based quantum computing. And of course, you'll hear firsthand from him in a moment. So yeah, thank you.
Thank you very much, Sophia, for that very inspiring talk. I don't know about you guys, but I particularly enjoyed the fact that you went through the maths very slowly at the beginning. That was very useful to understand the graph formalism later. Do we have any more questions? Yes, please, Jacopo.
So you mentioned that you need classical feedback for editing basically your graph state. What timescales are we talking about? And like what delay lines do you use? Are they dynamic delays or?
Yeah, so you need to feed forward, right, based on the measurement outcome. You need to adjust. That's very platform dependent, right? So if the time scale to measure and adjust your next measurement is slow compared to things like the coherence times, and you start computing that, that's a problem. Or with loss times if you're talking about photons. So it's very platform dependent, but it has to be a fast time scale compared to other relevant time scales in your experiment.
Maybe Julian?
Thanks. I was wondering what level of complexity we can reach, especially with these like atom systems, because I know for like photonics you can reach like few tens, I think, of photons entangled.
Yeah, so in principle, theoretically, it doesn't matter, right? As it doesn't for the photons. Like, so it's a technological limitation rather than a practical. I can tell you what people have done. So the largest one that I know of, at least, is this one from the REMPA group, where I think they go up to about 14 photons, which is quite nice, and I believe the 14 is for GHZ states. It's less than 20, I forget the exact number. But it's not easy to do this, right? So we have a lot of challenges on doing it probabilistically with photons, but there's also a lot of challenges on doing it this way. And there's things like, you need to catch the photons, right? So the photons could follow, they might not be even generated, they might follow another generation pathway, they might just go to the wrong direction. So you need a lot of engineering to make that work. And then another thing that we need to worry about, I think not yet experimentally, but as a theorist is something that we're looking into, is there's different types of errors happening on the emitter, non-Markovian errors, things like that. And those can transfer on, like I showed you in these diagrams, right? Like they can move over to the photons. And if they spread uncontrollably, that's a big problem. So we also have to worry about that. And all that will kind of determine what can you really practically do.
Thanks. We have time for one more quick question. Yes, please. Whoa, good catch.
You had some slide where you were comparing the circuit to the measurement-based, and if you have some fixed computation that you want to do, are the requirements in terms of entanglement comparable between the two models?
They're comparable in the sense that this is an efficient model, right? So you can do computation efficiently if you translate from circuit to measurement-based. But of course, it's not going to be a one-to-one correspondence. Because in the process, you need to consume some qubits. It also depends on the lattice structure. Sometimes some qubits are just measured away to get out of your path of entangling two particular ones. So it's not a one-to-one, but it's efficient. There's no like overhead that we worry about in terms of scalability or anything. They both scale, well. Yeah.
Thank you.
Okay, thank you very much. So I would just like to hand over a small token of our appreciation from MCQST and IMPRS. So thank you very much for your time today. Please, everyone, join me for thanking Sonia for her time, Sophia for her time. Sorry. So now we have the coffee break. There's no coffee break? Oh, sorry, okay, there's a bio break, but I think in principle the coffee machines still work. So try your luck. Sonia mentioned to me that there would be a group photo after the next talk. I think it's going to be on the roof. Instructions for how to get there will come after the next talk. Okay, see you back in about 10 minutes.